Hey everyone, welcome to The Explainer. Today, we're going to demystify one of the most incredible technological leaps of our modern era. I want you to think back to a time when your mobile phone was basically just a wireless landline. It was great for making voice calls, but it completely choked if you actually tried to pull up a web page. How in the world did we go from those slow, voice-centric 2G networks to the absolute data-driven powerhouse that is 3G? Well, it wasn't just some minor software tweak. It was a complete rewrite of the laws of wireless physics, all built on a foundation of WCDMA technology. So today we're going to unpack the invisible magic that literally made the modern mobile internet possible.
Okay, let's dive into our structural blueprint for today. First, we'll look at the leap to 3G. Second, we'll go inside the UTRAN architecture. Third, the WCDMA air interface. Fourth, we'll tackle multipath and soft handovers. And finally, turbocharging the whole network with HSPA.
All right, part 1, the leap to 3G and overcoming those frustrating 2G limits.
To really appreciate this leap, we have to understand the massive data bottleneck of the late 90s. Just look at this timeline. Back in 1991, GSM was a huge digital revolution for voice for sure, but for data, oh man, it crawled at a frustrating 9.6 kilobits per second. Even as engineers pushed 2G to its absolute breaking point with GPRS and edge packet-switched upgrades, they were maxing out in the low hundreds of kilobits. They literally hit a physical speed limit. The world desperately needed a revolutionary engineering solution to handle megabits of data for things like video and internet browsing. Enter 3G, which ultimately scaled up to an astonishing 14.4 megabits per second with HSDPA.
So, what was the secret sauce? It's all about changing how phones share the airwaves. 2G GSM used TDMA, or Time Division Multiple Access. I want you to imagine a crowded room where everyone has to wait for their specific fraction of a second to speak. It's orderly, yes. Fast? Absolutely not. 3G completely flipped the script by introducing WCDMA, Wideband Code Division Multiple Access. Instead of waiting turns, imagine everyone in that crowded room talking at the exact same time, but every single conversation is happening in a completely different, unique language. You only hear the language you actually understand. The rest just sounds like background noise. In engineering terms, this is called variable orthogonal spreading, and it completely blew the doors off the network's capacity.
Moving right along to Section 2, inside the UTRAN architecture, looking at the physical network hardware. So, what kind of physical hardware is actually required to process all these simultaneous signals? Well, this diagram provides a spatial map for the entire Universal Terrestrial Radio Access Network, or UTRAN for short. If you look down at the bottom left, you see the user equipment connecting over the air to the Node B. Those Node Bs are wired directly into the radio network controllers, or RNCs, which then interface with the larger core networks. And notice those little labels, IUB, IOR, IUPS. Those are the specific ATM-based interfaces connecting all this hardware together. Let's quickly break down the three main stars of this show.
First up, we have the user equipment, or UE. This is the starting point of our signals journey. It's pretty straightforward. It's simply the combination of your physical mobile equipment, meaning your actual phone, and your USIM card, which securely identifies you to the whole network.
Next, we hit the Node B. In 3G terminology, Node B is basically the base station. It's the physical antenna tower you see outside, plus the processing equipment sitting right at the base of it. The Node B is responsible for actually blasting out and receiving those WCDMA radio signals across the air interface, supporting both FDD and TDD modes.
And then we have the RNC, the Radio Network Controller. And I want to emphasize the word controller here. The RNC acts as the absolute brain of the operation. It manages multiple Node Bs, it switches ATM data cells, handles network congestion, and manages the incredibly complex task of passing your ongoing call from one cell tower to the next as you're driving down the highway.
All right, Section 3, the WCDMA air interface, where we get into the invisible physics.
Hardware is cool and all, but the true genius of 3G lies in the invisible physics of the radio waves. Notice how the original narrow data signal on the left is mathematically multiplied with a high-speed spreading code. This transforms your narrow signal into a very wide-band signal. That's exactly where the W in WCDMA comes from. Because the signal is spread out over such a massive frequency band, it becomes incredibly robust and highly resistant to interference. When it hits the receiver on the right, the network uses the exact same code to despread it, recovering your original data perfectly.
But honestly, this raises a massive question. If every single user in the cell is transmitting on the exact same wideband frequency at the exact same time, how does the system not just collapse into a wall of deafening radio noise? I mean, if one phone is closer to the tower than another, wouldn't its signal just completely drown everyone else?
The fix for this is a hyper-aggressive system of power control. To minimize that interference, WCDMA basically forces every phone to whisper as quietly as physically possible while still being heard by the tower. It's a two-part team effort. The RNC manages the outer loop, setting a target quality level. But the Node B manages the inner loop, a crazy fast power control that actually commands your phone to adjust its transmission power up or down 1,500 times per second. Yes, per second. This ensures no single phone ever overpowers the shared airspace.
Moving to Section 4, multipath and soft handovers, or how we finally stopped dropping so many calls.
Let's look at how 3G engineers took one of the most frustrating problems in radio physics, bouncing signals, and turned it into a literal superpower. When your phone transmits a signal in a dense city, that signal bounces off buildings, arriving at the cell tower at slightly different times. Older 2G networks got completely confused by these echoes. WCDMA introduced the rake receiver. Think of it quite literally like a garden rake. Instead of being confused by scattered signals, the multiple fingers of the rake receiver actively gather up those different multipath echoes, align them mathematically using their spreading codes, and actually combine them to make the final signal stronger.
And because the rake receiver is so good at listening to multiple signal paths at once, your phone can actually connect to two completely different Node Bs at the exact same time. Notice here how the phone is transmitting to both base station 1 and base station 2 simultaneously. The RNC then takes the signals from both of those towers and merges them into one seamless data stream.
This is known as a soft handover, or macro diversity. Back in the 2G days, handing off a call from one tower to another was a break-before-make situation. You had to disconnect from Tower A before connecting to Tower B, which naturally caused dropped calls. 3G's soft handover is make before break. You are actively linked to both towers until you are completely and safely in the new cell. It was the ultimate engineering cure for the dropped call epidemic.
Finally, Section 5, turbocharging with HSPA and breaking those speed limits.
WCDMA was a brilliant foundation, no doubt, but to keep up with our exponential hunger for mobile data, 3G had to evolve. Enter HSDPA. Engineers realized the RNC was simply too far away in the network to make split-second bandwidth decisions. So, notice the new protocol layer here called MAC-HS. They introduced this right at the edge of the network, physically inside the Node B itself. This allowed the Node B to react to channel quality feedback from your phone with lightning-fast scheduling, optimizing data delivery literally on the fly.
A real game changer implemented at this edge layer is Hybrid ARQ, or HARQ. It's a highly efficient stop-and-wait error correction system. It works like this. Step 1, the Node B sends a packet of data. Step 2, if there's an error over the air interface, it's detected immediately. Step 3, because HARQ operates right there at the Node B, it fast requests a retransmission in mere milliseconds. It even mathematically combines the corrupted packet with the retransmitted packet to salvage the data. This massively reduced latency.
To put this into perspective, just look at the sheer magnitude of what these packet-switched upgrades accomplished. We started at 9.6 kilobits in the GSM era. The first release of 3G UMTS pushed that to a respectable 384 kilobits. But once HSDPA was introduced, downlink speeds rocketed up to 14.4 megabits per second, with HSUPA pulling the uplink to 5.76 megabits per second. That is just a staggering leap in everyday performance.
And they definitely didn't stop there. The final boss of the 3G era was HSPA+. Engineers squeezed absolutely every last theoretical drop of efficiency out of the standard. They disabled the old variable spreading factor, brought in highly efficient adaptive modulation encoding, implemented incredibly fast 10-millisecond scheduling, and crucially deployed MIMO, multiple input, multiple output antennas, to essentially double the data pathways using the exact same radio spectrum.
So, the engineering journey of 3G really is a masterclass in solving impossible physics problems with elegant mathematics and clever network design. But, as we know, telecommunications never sleeps. If WCDMA and HSPA pushed spread-spectrum radio waves to their absolute theoretical limits to give us the mobile internet, what invisible physical barriers will the engineers of 4G have to break to give us the speeds of tomorrow? Well, that is a topic for our next explainer. Thanks so much for joining me today, and keep questioning the technology around you.